Okay, today we are going to start a new topic, excavating and lifting. Can you hear me?
Yes, Professor.
Okay, so this is the topic 7 of this course, and it has been taken from chapter number 3 of the textbook. So, excavating and lifting equipment. So, we will, in this topic, we will look at various types of equipments. And these equipment will be related with the excavating and lifting operations in the construction. So a family of such equipment is called an excavator. An excavator is defined as a power-driven digging machine. So the purpose of excavator is to dig the soil. That means if the soil is in its natural state on the ground, that excavator will dig it for us. And then, of course, after digging the soil, it has the excavator will also load the soil into the loading trucks. So, major types of excavators used in earth moving operations include hydraulic excavators and the members of the cable operated crane shovel family, which are called as the shovels, drag lines, hose, and clamshells. So excavator is not just one equipment. Excavator is a type of different equipments. So which include these different types of equipments. Examples are dozers, loaders, and scrapers can also serve as excavators. Okay, although they have some other main functions as well for dozers, loaders, and scrapers. But sometimes the equipment may have some multi-functions as well. That means the equipment may perform more than one function. For example, the dozer, whose main task is to track the machine and track the material. That means push or pull the material or other equipment. But dozers may also serve as for excavator as well. So this is a series of like 3 chapters which we will look at in this course, and in those chapters we will be looking at such different types of materials, different types of equipments. Okay, so what are the excavators and crane shovels? So a crane shovel is a family of cable operated construction machines. So members of this family include the shovel, backhoe, drag line, clamshell, mobile crane, and pile driver. So these machines may work with the help of the cables. That means those cables will provide the resistance to load or to lift the materials. In addition to cables, there may be the hydraulic excavator as well. So in recent times, the hydraulic excavators have largely replaced the cable-operated crane shovel family. The advantages of hydraulic excavators over cable-operated machines are faster cycle time, a higher bucket penetrating force, more precise digging, and easier operator control. So if we compare the cable operated machines and the hydraulic operated machines, hydraulic operated machines are more efficient and powerful. Hydraulic telescoping boom mobile cranes are also used. So the telescoping boom mobile crane, that means those cranes whose boom length can be changed, like the uh, uh, change of the length of a telescope. Okay. The major remaining cable-operated machines based on the original crane shovel are the dragline and the mobile lattice boom crane. So all of these different equipment we will look at in this topic. Excavators and crane shovels consist of three major assemblies: a carrier or mounting, a revolving superstructure containing the power and the control units, also called as the revolving deck or turntable, and a front end assembly. So we will see a picture later on, which will involve all these different components. Carriers available include are the crawler, truck, and the wheel mountings, as shown in this figure 3-2. The crawler mounting provides excellent on-site mobility, and its low ground pressure enables it to operate in areas of low trafficability. So these machines, like most of the construction equipment which move on the ground or on the construction side, are either wheel mounted or crawler mounted. Crawler mounted equipment is useful in those areas where the soil condition is soft, and that means the conditions are for low trafficability. So the low bearing capacity soils, in those types of sites, there's crawler mounted machines may be used. So the crawler mounting are widely used for drainage and trenching work, as well as for rock excavation. Truck and wheel mounting provides greater mobility between job sites, but are less stable than crawler mountings and require better surfaces over which to operate. So if the earth moving operations involve larger areas in which the soil have to move over a longer distance, then truck and wheel mounting may be better. But in those situations, the trafficability conditions should be also better, because the stability of the wheel mounted equipment is less than the crawler mounted equipment, due to the obvious reasons that the crawler mounted equipment has more contact surface with the ground. The truck mountings use a modified truck chassis as a carrier, and thus have separate stations for operating the carrier and revolving the superstructure. So the truck mounted and the wheel mountings are two separate types. In the truck mountings, there is a separate position for the operating the carrier and revolving the superstructure. Wheel mountings, on the other hand, use a single operator station to control both the carrier and the excavating mechanisms. So truck mountings are capable of highway travel of about 50 miles or about 80 km per hour or more, whereas the wheel mountings are usually limited to about 48 km per hour or less. So here are some of these pictures of these equipment. So this picture shows a hydraulic excavator. So as you can see that this is a crawler mounted excavator, and this crawler mounted excavator can excavate below the surface. That means on the surface at which the crawler mounted excavator has been placed, and below that surface, it can excavate it. This is the schematic diagram of three types of mountings. So, so this revolving superstructure, okay, can be mounted on either the truck, or it can be also mounted on the crawler, or it may also be mounted on the some wheel mounting, and then it may be also, and then later on it may be pulled by some other machinery or some other truck or some tractor. So these are the three different types of crane, shovel mounting, and revolving superstructure. Okay, so our main purpose from the calculation point of view, or from the learning point of view, is to find the production of the each of those equipment which we are going to study. So as far as the excavator production is concerned, the excavator production will depend on the bucket rating. So bucket is the component of the excavator which will hold the soil. So since bucket rating for cable shovel, drag line, and cable backhoe are based on truck volume, it is often assumed that the heaping of the buckets will compensate for the swell of the soil. That means normally the bucket will have a fixed volume, and that fixed volume will be 1 cubic meter. Okay, that 1 cubic meter will be the struck volume. That means when the bucket is fully covered, okay, and then all the material is being placed in the space in the bucket. However, in practicality, the bucket when the bucket will be used for digging the soil will heap over the bucket. So in that case, an assumption can be made that the heaping of the bucket will compensate for the swell of the soil. That means whatever the soil will swell, and then as a result of the swell, there will be some heaping of the soil. So which will mean that although the heaped volume of the soil may be the same as maybe more than the bucket volume, but due to the swelling, we may assume that, for example, a 5 cubic yard bucket would be assumed to actually hold a 5 cubic yard of material. So although that 5 cubic yard material in the bucket will be in the loose condition, and it will it will be in the heaped condition, and the overall loose volume will be more than that. So, but we may assume that. So it may be a simple assumption for this purpose. A better estimate of the volume of material in one bucket load will be obtained if the nominal bucket volume is multiplied by a bucket fill factor or bucket efficiency factor. Although, of course, we can use this assumption, but a better estimate can be by the some parameter which is called as the bucket fill factor. So the suggested values of the bucket fill factor for common soils are given in this in the next table. So table, this is the table for the bucket fill factor. So for example, this is the table for the bucket fill factor. So the bucket fill factor depends on the type of the material. So for example, if it is a common earth or loam, the bucket fill factor can be taken between 0.8 to 1.1. If it is a sand and gravel, the bucket fill factor may be taken about 0.921. That means whatever the volume of the bucket, you can take this bucket fill factor and then you can multiply it with that, and then you can take the amount of the load in one time in the bucket. So as an example, we see that estimate the actual bucket load in the bank cubic yards for a loader bucket whose heaped capacity is 3.82 cubic meter. The soil's bucket fill factor is 0.9 and its load factor is 0.8. So the bucket load is equal to, in this case, will be equal to 3.82 cubic meter times 0.9. So this is the bucket fill factor. That means it will be 3.44 loose cubic meter. But 3.44 loose cubic meter will be equal to 2.75 bank cubic meter. So from the loose cubic meter, if we want to find the bank cubic meter, we will multiply by the load factor. So this load factor formula we have seen in this in the previous topic. Okay, so if we want to convert the loose volume into the bank volume, then we will multiply the loose volume with the load factor. So 3.82 cubic meter volume, that means the bucket is actually 3.44 cubic meter. Okay, that is the heaped capacity is 3.82 cubic meter. So that means 3.82 cubic meter heaped capacity of the bucket will actually hold about 3.44 loose cubic meter. Okay, and then that 3.44 loose cubic meter is actually equal to about 2.75 bank cubic meter. That means if we have to excavate 2.75 bank cubic meter, then this bucket can be used, but the volume in that bucket will be then that 2.75 bank cubic meter will be equivalent to its heaped capacity for the bucket. Okay, hydraulic excavator. Operation and employment. So what are the steps or precautions we can take in those hydraulic excavators? So the original and most common form of hydraulically powered excavator is the hydraulic excavator equipped with a hoe front end. So this machine is also called as the hydraulic hoe or hydraulic excavator backhoe. So a backhoe or simply a hoe is an excavator designed primarily for excavation below grade, as we have seen in one of the figures of the equipment before. As the name implies, it digs by pulling the dipper back towards the machine. Okay, so that's why its name is called as the backhoe. So the components of the hydraulic excavator are illustrated in figure 3-3. So in this machine, the boom and dipper arms are raised and lowered by hydraulic cylinders. So in addition, the dipper is pivoted at the end of the dipper arm so that a wrist-like action is provided. So when the dipper is filled, the dipper is curled up to reduce the spillage, and the boom is raised and swung into the unloading position. The load is then dumped by swinging the dipper up and away from the machine. So this is the operation of the backhoe operation machine. So as you can see that you may have seen this machine many times on the construction site. So the backhoe is widely utilized for trenching work. So so we have the boom here, okay, and then this is the stick or dipper arm cylinder, okay, And then over on the front end, there is the stick or dipper arm over here as well. So, and the bucket or dipper cylinder over here as well. So you can see that different types of dipper cylinders provide different type of motion. So if we want to move, if we want to rotate this bucket into this direction, over around this axis over here, then this type of dipper arm will be moved. If the boom have to be raised up or down, then the attachment hoist cylinders should have to be moved. So basically, there are three types of motion which can be made by this machine. And then, of course, there can be the rotating motion at the hoist, at the mounting assembly as well. And in this dipper or the bucket, the material may be placed when excavating. So this was the simple explanation of the hydraulic excavator. So you can see that various kinds of motions in this hydraulic excavator are achieved with the one or with two or more different types of dipper cylinders. So this dipper cylinder, bucket or dipper cylinder, okay, stick or dipper arm, okay, and then this is also called the stick or dipper arm, okay. So, and this is the stick or dipper arm cylinder. So this is called as the stick, okay, and boom, and different types of motions for the cylinder can be placed. So another type of the hydraulic excavator is the telescoping boom hydraulic excavator. So this telescoping boom hydraulic excavator, as the excavator which is shown over here, it is a crawler mounted excavator. Okay, it is a crawler mounted excavator. This is the mounting assembly which can rotate horizontally. This these crawlers will help the excavator move up or down, or move front or backward. And then this telescoping boom may change its length, okay, so that this mounted bucket over here can move to a longer and shorter distance. So this telescoping boom may be used for those situations when we need to, more reach to the excavating materials. So a special form of the hydraulic excavator which utilizes a rigid telescoping boom in place of the boom and dipper arm of the conventional hydraulic backhoe is shown here. These machines are very versatile and capable of ditching, sloping, finishing, cleaning ditches, ripping, and demolishing, as well as trenching. So the reach of these machines may be much longer than the previous machine over here. Okay? So if you want to increase the reach, then that means the telescoping boom may be extended over here. So the use of compact or mini excavating equipment is a growing trend in the construction equipment industry, as well as hydraulically powered mini excavators. So excavators are normally large machines, but for smaller works, mini excavators may also be used. The advantages of such equipment include compact size, hydraulic power, lightweight, maneuverability, and versatility. So a typical mini excavator is illustrated in figure 3-5. So these machines are available in sizes for about 7.5 to 45 kilowatt, or about 10 to 60 horsepower, with digging depths from about 7 to 15 feet, or about 2.1 to 4.6 meter. So although these digging lengths are 2.1 to 4.6 meter, they are quite appreciable, but compared with the normal size of the excavator, these machines are relatively smaller. So some machines are as narrow as about 0.74 meter, making them very useful for excavating in confined spaces. So the mini excavator's ability to operate with the full 360-degree swing, their hydraulic power and their low ground pressure have resulted in their replacing backhoe or loaders in some applications. So when equipped with the dozer blade, they may also be employed in leveling, grading, backfilling, and general job cleanup. Okay, so this is the picture of a mini excavator. Okay. So as you can see that although it's not that mini, but you can see that compared with the previous models which were shown, this machine is relatively small. So for smaller amounts of work where we do not need to make very deep trenches, these types of excavators can be moved. So in this case, the machine is probably making a trench. So that means starting from here and then going in towards in that direction. So with the progress of the work, the machine may move backward, okay, and then that digging arm over here may provide the digging operation, and then with the rotation of that digging arm, then that load which has been put into the machine may be dumped into the loading truck, and then that material may be moved away from the site, or that material may be dumped alongside this trench for later use on the site. Okay, so how do we estimate the production of such machines? So there is a general formula for the production of such machines, which is called as the production of such machine is called as the C times S times V times B times E. So production may be estimated by using this equation together with the two other tables, 3-3 and 3-4. So C times S times V times B times E, what are these parameters? So C is the number of cycles per hour. So first of all, we have to estimate how many cycles of operations a machine can make. So just like this over here, if this machine is working, so what will be its cycle? Its cycle will start when that machine digs it, okay, and then after digging it, it rotate to some other location and then dump that material back, and then come back and then to dig it again. So the work will be performed in a cyclic manner. So we have to estimate the time for the cycle. Okay, how many cycles per hour? So this number of cycles per hour can be estimated using this table 3-3. But remember that, and you may have also seen in some other problems in the previous chapters as well, estimation of the different quantities is, for example, the cycle time, as it has been said over here, it can be seen from this table. The cycle time can be seen from the table, but there may be some other ways for the calculation of the cycle times, which may involve some more direct observations as well. Okay, but in this case, just maybe we can use this cycle time, and then multiplied by the S is the swing depth factor. So swing depth factor, that can be also seen from the table 3-4. So that means because this type of machine will dig deeper, that means below the surface on which the machine is mounting, and it may also, after digging the machine, it will lift it and then swing it and then to dump at some other place as well. So what will be the angle of the swing over here? That may be placed over here. So more is the depth, more is the swing, and more less will be the swing depth factor for the calculation of the productivity. That we will see from the table 3-4. So this factor multiplied by this factor, and V is the heaped bucket volume. So if there is in one cycle there will be one bucket volume that will be placed, and then B and E are the B is the bucket fill factor. B is the bucket fill factor. So as we have seen before in table 3-2, it depends on the type of soil, and E is the job efficiency. So that means how efficiently the job is being performed. So for example, in 1 hour total duration, how many minutes the machine is working. So for example, in 1 hour total operation, the machine was operational for like 45 minutes. So the job efficiency in this case will be 45 divided by 60. That will be 0.75. So that job efficiency will also have to be estimated. So if you multiply all those factors, so then you will get a production in terms of the loose cubic yard or loose cubic meter per hour, depending on the how the bucket volume is measured. So because since we have the cycles per hour, so that means this type of formula will give us directly the answer in terms of the cubic meter per hour. So then let's see what are those C and S value factors. So C is the cycles per hour. So for standard cycles per hour for the hydraulic excavators. So if we are using the hydraulic excavators, their standard cycles per hour are based on the type of the material, okay? Based on whether they are the wheel tractor, or based on whether they are, what is the size of the machine. So if there is a medium size excavator, and if there is a medium size excavator and the soil is tough clay, so then we have 130 cycles per hour. So it can perform as much as 130 cycles per hour. That means less than a minute for 2 cycles per hour per minute. Okay, that means in 1 minute there are more than 2 cycles in that case. So that means this operation can be performed. Okay, so these are the standard cycles per hour. However, these standard cycles per hour are based on some certain swing and depth conditions. So we have to adjust for the swing and depth as well. So if the depth of the cutting is percentage of the maximum is 30, 50, 70, that means for each type of machine, there will be the maximum depth that will be rated for that machine. Okay, and then if we are going into the 30, 50, 70% of that depth, and then for different angles of swing, that means 45, 60, 50 degree angle of swing, we may estimate, we may look at the value. So for example, if the angle of swing is 90 degree and the depth of cut is about 50% of the maximum, so then in that case, swing depth factor will be 1.1, which means that we are swinging and cutting less than its rated capacity. So therefore, in that case, the production will increase. But for larger depths and larger angles of swing, the swing depth factor will be the minimum. So highest is for this only 30% and 45 will be 1.33, but the lowest is 0.75. So the values are decreasing downward and towards right in this table. Okay. So this is the example 3-2 for the application of this equation CSVBE. Okay, CSVBE. So find the expected production in loose cubic yards or meters per hour for a small hydraulic excavator. A heaped bucket capacity is 3/4 of a cubic yard or 0.57 cubic meter. The material is sand and gravel with a bucket fill factor of 0.95. So the job efficiency is 50 minutes per hour. The average depth of the cut is 14 feet or about 4.3 meter. Maximum depth of the cut is about 20 feet or 6.1 meter. And the average swing is 90 degrees. So you can see that we have various types of data over here. The cycle output is 250 cycles per 60 minutes. So this we can obtain from table 3-3. So how did we obtain? It is a, what type of excavator? Small hydraulic excavator. It is a small hydraulic excavator. Okay. So for the small hydraulic excavator, we have this. And the material is sand. Okay. The material is sand. Sand. So for this, we got 250. So this is the standard cycles per hour. Okay. So we have got the value of S. The swing depth factor is 1. Why? Because that depends on the angle. So for example, 4.3 divided by 6.1. So this is how many percentage? So 4.3 divided by 6.1 is about 4 by 6, 0.67, okay, 0.7%, okay? About 0.7%. And then the angle of swing is 90 degree. So we can see from the 90 degree angle and then from 70%, it is about 1.00. Okay. So the swing depth factor is 1. So C is 250, S is 1. The bucket volume is 0.57 cubic meter, okay, which is given. Bucket fill factor is 0.95. So job efficiency is 50 divided by 60, that is 0.833. So now the production will be C, the value of C, this is C, this is S, this is V, but that V, it is the heaped volume. So we have to multiply it with the bucket fill factor to calculate the actual volume, okay, for the bucket, which has been placed. So that means if it is 0.75, actually it will fill it like 0.95. And then multiply it by 0.833, which is the job efficiency. So C, S, V, and B, okay. B was over here. So C, S, V, B. So B is the bucket fill factor. So we have to multiply it by B. So everything will be multiplied together, 250 by 1 by 0.57 multiplied by 0.95, 0.833. So in this case, we will get about 113 loose cubic meter per hour. Okay, 113 loose cubic meter per hour as the production of the hydraulic excavator. Okay, so these were the hydraulic excavators. So now the next type of equipments are the shovels. So their production is also similar to the hydraulic excavator. Do you want to ask anything? Any question? Okay, so after the hydraulic excavators, let's look at another type of material, which is equipment, which is called as the shovels. So these are called as the hydraulic shovel. Okay, and let's look at what the shovels are. So shovel, the hydraulic shovel is also called a front shovel or hydraulic excavator front shovel. The hydraulic shovel digs in with a combination of crowding force and breakout or prying force. So the crowding force is generated by their stick cylinder and the acts as at the bucket edge on it, tangent to the arc of the radius from point A. So the breakout force is generated by the bucket cylinder and acts at the bucket edge on the tangent to the arc of the radius through point B. Okay, later on in the figure, it will be shown that what are these points A and B. So shovel has a limited ability to dig below the track level. So it is most efficient when digging above the track level. So remember that we are using the hydraulic excavators or the backhoes for digging below the track level. But if we want to dig above the track levels, then shovels are used. So the shovel should have a vertical face to dig against for most effective digging. So this surface known as the digging face is easily formed when excavating a bank or hillside. So when the material to be excavated is located below the ground level, the shovel must dig a ramp down into the material until a digging face of the suitable height is created. So the process is known as the ramping down. Okay. So the production of hydraulic shovels may be estimated using this equation, which is similar to the previous equation, CSVBE. Okay, CSVBE. C is the cycles per hour as before. S is the swing factor. So in this case, it is not the swing depth factor, it is the swing factor only, because the shovels do not dig below the track level. So there is no depth involved. Okay, so there is only a swing factor over here. And V is the heap bucket volume, B is the bucket fill factor, and the E is the job efficiency as before. So the only difference between the determination of the quantities between this formula and the previous formula is that the swing factor is different over here in the case of shovels. Okay, so what are those components in the shovel? So as you can see that in the shovel, this bucket face is towards the front of the machine. In the case of the backhoe, the bucket face was towards the towards the machine. Okay, here it is away from the machine. The bucket factor. So the other components are relatively similar to the hydraulic excavator or the backhoe. So here is the explanation of the points A and B. So digging action of a hydraulic cylinder. So the breakout force, there is a breakout force and there is a crowding force. So the crowding force is applied when the movement is movement takes place around the point A, and the breakout force is provided when the movement takes around the point B. Okay, so these two types of movements provide the force for the digging action. Okay, and then this is the table which can be used for the calculation of the cycle for the determination of the cycle time of the shovel. So similar to the hydraulic excavator, for the shovels we have the small, medium, and the large size shovels. And on the other hand, we have the type of material. So in this case, then we can choose the cycles per hour using this table. Here, for the swing angle, that is for the factor S, we can use this table for the shovels. So as an example, so we have, in this case, a 2.3 cubic meter hydraulic shovel. So for a 2.3 cubic meter hydraulic shovel, and the type of material is common earth. So if it is a 2.3 cubic meter hydraulic shovel, 2.3 is small, and whether it is a bottom dump or front dump, so that we need to see. Yeah, front dump, it is a front dump. Okay, so front dump, 2.3 cubic meter small shovel, and it is in a common earth, so the number of cycles will be 150 cycles per hour. 150 cycles per hour. Okay, and or 150 cycles per 60 minutes. The swing factor will be 1.05. It is because the average angle of the swing is 75 degrees. So swing factor is 1.05. The bucket volume is 2.3 loose cubic meter. The bucket fill factor is 1.0, that is given, or it may be seen from the table as well. And the job efficiency is also given as 0.8. So just simply multiply 150 with 1.05 with 22.3 with 1 and 0.8. We get a production of 290 loose cubic meters per hour in this case, for the case of shower. So this example is very similar to the previous example 3-2. Okay, now let's look at the third type of equipment which we want to see in this topic, which are the drag lines. So drag lines is a very versatile machine that has the longest reach for digging and dumping of any member of the crane shovel family. So it can dig from above the machine level to significant depths in soft to medium hard materials. So the bucket teeth and weight produce digging action as the drag cable pulls the bucket across the ground surface. So the digging is also controlled by the position at which the drag chain is attached to the bucket. So the drag line does not have the positive digging action or the lateral control of the shovel. Hence, the bucket may bounce or move sideways during the hard digging. So also more spillage must be expected in loading operations than would occur with the shovel. So drag line is another excavating material equipment. Its use is also there in those situations when we need a longer reach, okay, and where the normal hydraulic excavators or the shovels may not provide us the desired operations due to the uh, approach of the material is not that convenient. So, but their disadvantage is that the drag lines can only drag the buckets towards the machine. They cannot have the sideways, they cannot have the sideways actions and the front actions over here, because the drag lines provides its force or its power due to the weight of the bucket and also to the pulling action of the cable. So this is how the drag line looks like. So drag line is similar to a crane, but that over here you can see that this is the bucket. So this bucket is usually quite heavy, and when that bucket is applied on that material, is placed on that material, then due to these two cables, one of this cable, the other is this drag cable, the force is applied on the bucket, and then with that force, the bucket is then filled with the material. Okay, so then that bucket is filled with the material, and then that bucket is raised, and then the excavated material is then placed elsewhere. So these are the components of the drag line. So it has hoist cable, boom hoist cable, boom, etc., and then these components provides the dragging action. So this is another view for the drag line bucket. So more detail for the drag line bucket. So there is this drag chain, and then there's this dump cable. That means if this cable will be pulled, then this material can be dumped together. And then if if there is this drag chain, then this drag chain will provide the dragging action. With this dragging action, the material will be filled into this bucket. And this another one is the hoist chain. Hoist chain will lift the bucket up. So in this way, this drag line will work. The drag line is most effective in its digging area, which is about 15-degree front and back to the drag line, because drag line basically rotates over here in this area. Okay? So the effect of rotation outside of this area is not very efficient. So therefore, a larger, a special skill is required to operate the drag lines, so that an operator can operate it in a more efficient manner. Okay. So here is this table which can be used to find the ideal drag line output in bank cubic yard or bank cubic yard meter per meter. So this is so in this drag line, we can using this table we can find the production the level we can find the output of the drag lines. Okay, so based on the bucket size and based on the type of the material as well. And then the drag line can be used not only for the over the surface, but at some greater depths as well. Also, there is a table for the optimum depth of cut for short boom. Okay, so for the drag line there is a bucket size, and then the type of the material, and then it will tell us that this will be the optimum depth of the cut for the drag lines. And then for the drag lines, there is also a swing depth factor as well. So which for this swing depth factor for the drag lines, this table can be used. So how to estimate the production of the drag line? To estimate the drag line production using the table, so determine the ideal output first of the drag line for the machine size and material using table 3-7, and then adjust this figure by multiplying it by its swing depth factor, table 3, and then the job efficiency factor as shown in figure 3-3. So the expected production for the drag line, the equation is not like CSVBE as before, it's different. It has from the table, you will find the ideal output. This ideal output will be then multiplied by the swing depth factor, and then it will be multiplied by the efficiency. So this ideal output will take care of the cycles and the bucket fill factor. So in this way, this is the equation for the expected production for the drag line, which is different from the previous two equations. So here we can do some example. Determine the expected drag line production in loose cubic meters, meters per hour based on the following information. So the drag line size is 1.53 cubic meter, swing angle is 120 degree, average depth of cut is 2.4 meter, material is common earth, and job efficiency is 50 minutes per hour. So the ideal output from table 3-7 will be 176 bank cubic meter. Okay, so let's see the ideal output. Okay, so remember that the drag line size is 1.53 cubic meter, and 1.53 cubic meter, and so 1.53 cubic meter. Table 3-7. So ideal drag line output. So that it is 1.53. So 1.53. So which value we are going to take? 265, 230, 195, 145. So that will depend on the type of the material. Okay. So type of the material is common earth. Yes, common earth. So 1.53 in type of material. So what is 1.53? And common earth is this. So the production is 176 loose cubic meter per hour. So the production is ideal output is 176. Remember that. Okay. In the previous two cases, we get the volume in terms of the loose cubic meter, but this table is giving us the volume in terms of the bank cubic meter. Okay, so this you should remember that. So this is giving us in terms of the bank cubic meter per hour. As you can see that in this table 3-7, it is in terms of the bank cubic meter per hour. Okay, 176. So now we have this ideal output in terms of the bank cubic meter per hour, we need to find the swing depth factor. So swing depth factor is 120 degree. The average depth of the cut is 2.4 meters. So we will look at the table. Swing depth factor. So it is 1.53 optimum depth of cut for the short boom. So first we will find the optimum depth. So 1.53 meter. Then the optimum depth is 3 meter over here. And then this swing depth factor is based on this. So we have, so from this table 3-8, we will find the optimum depth of this for the boom. So that means for the common earth, and we will get 3 meter for the bucket size of 1.53 meters. So 3 meter. And then in our problem, what we have over here is optimum depth of the cut is given as 3 meter, which is fine. Actual depth divided by the optimum depth. So actual depth is given as average depth of the cut, which is needed, is about 2.4 meters. So 2.4 divided by the optimum, so which is 80%. Okay. So now we will use this table 3-9 again for the swing depth factor. So it is 80%. And then what is the angle of swing? So for this angle of swing, we have to look at again 120 degree. So 120 degree and 80%, we will get a factor of 0.9. Okay. So this is the swing depth factor 0.9. So earlier we calculated the ideal output and we calculated the swing depth factor. And the job efficiency is 50 minutes per hour, 50 minutes divided by 60. So that is 0.833. Okay, so now what we have over here is 276 is the ideal output in bank cubic meter, multiplied by the swing depth factor, which we have found as 0.9, multiplied by 0.833, which is the job efficiency. So this is the bank cubic meter. And we have to multiply it with 1.25, which is the 25%, which will be the swell. This 1.25. To convert this volume into loose cubic meter per hour. This 1.25 cubic meter, that is 1.25 or the 25% swell has not been given this in this table. But we know that from our previous topic, from the previous chapter, we know that this swell was, swell for the common earth is about 25%. So we can use this value. So the loose bank cubic meter is to be multiplied by this swell factor. So then it will be 1.25. So the loose volume will be 165 loose cubic meter per hour. So although in this case, you can see that the formula is relatively simple than before, but we need to look at 3 tables. And if we also have to look at the table for the swell factors, then swell factors, then you have to look at 4 tables to use this formula, okay, for the drag line. Okay, so these were the drag lines. And the 4th type of equipment which we are going to use or which we are going to discuss over here is the clam shells. So when the crane shovel is equipped with the crane boom and clamshell bucket, it becomes an excavator known as the clamshell. Okay, so basically it is a variation of the previous equipment. So on the crane we can put another type of bucket which is known as the clamshell. So the clamshell is capable of excavating to great depths, but lacks the positive digging action and precise lateral control of the shovel and bucket and the backhoe. So clamshells are normally used for excavating vertical shafts and footing and unloading bulk materials from rail cars and ships, and moving bulk materials from the stockpiles to bins, hoppers, or all units. So this is the schematic diagram of the clamshell. So here you can see that it is uh, the bucket is like uh, like the mouth of a clam. Okay, that means the clam can open its mouth over here, and then that mouth can be closed down. So for digging it, this mouth can be opened, and then when the material has been dug, then that mouth can be closed, and then it can be lifted up using this crane operations. So the operations for this clamshell will be main operation for the digging and holding the material can be controlled by this drag line and the other holding line and the closing line for the clamshells as well. So this is another view of the clamshell. So you can see that many cables are here due to the movement of these cables. This assembly can be opened and closed down. Okay, and this is another type of clamshell. So this is called as the orange peel bucket. So it's the shape is like an orange peel. Okay? This orange peel bucket is principally utilized for underwater excavation and for rock placement. Because of its circular shape, it is also well suited to excavating piers and shafts. It operates on the same principle as does the clamshells. Okay, so how is its production measured? So that has been illustrated over here with the help of this example 3-5. So estimate the production in loose cubic yards per hour for a medium weight clamshell excavating loose earth. So heaped bucket capacity is 1 cubic yard or about 0.75 cubic meter. The soil is common earth with a bucket fill factor of 0.95. So estimated cycle time is 40 seconds. The job efficiency is estimated to be 50 minutes per hour. So no specific formula has been used, but here you can see that the cycle time has been given. Since the cycle time has been given as 40 seconds, so we know that in 1 hour there are 3600 seconds. So that means in 1 hour, then there will be 3600 divided by 40 cycles. Okay, 40 cycles. So this is the cycle number of cycles per hour multiplied by the volume, that is the volume of the bucket. There is no swing factor over here because this type of equipment does not need to have any swing over here. So or in this case, actually the swing factor has been already considered in terms of the cycle time. So therefore we are not considering any swing depth factor. So 36, so this is the cycle time multiplied by 0.75, and then the bucket fill factor is the 0.95. So this is over here. So for example, if we just want to visualize the formula, so the normal formula is like this. So the production formula is C times S times V times B times E. So here C times S has been given as 3600 by 40. V is the volume of the bucket is 0.75, and B is the bucket fill factor, which is 0.95, and the job efficiency is 50 by 100. That means 50 minutes of work in 60 seconds. So multiply everything together, so then we get the volume in terms of the 53 loose cubic meter per hour. Okay, 53 loose cubic meter per hour. So 3 loose cubic meter per hour. Okay. So in this case, the production of the machine can be calculated. Okay, now we have some more machines regarding the excavations. So one of the operations in the construction is the trenching operation. So the trenching operation, and then on the other hand, there are some technologies in which there is no need to make the trenches. So these are called as the trenchless technologies. So there is a growing demand for the methods of installing utility systems below the ground with minimum open excavations. So some methods available for achieving this goal include the specialized trenching machines and plows, as well as trenchless technologies, also called as the trenchless excavation. So there are certain trenching machines and plows. Some of these types of trenching machines available include the chain trenchers, ladder trenchers, and bucket wheel trenchers. So the figure, which is on the next page, will show a large chain trencher capable of digging 14 to 16-inch wide vertical side trenches to a depth of about 10 feet, that is about 3.1 meter. The ladder trenchers are similar to the chain trenchers but are larger. They are capable of digging trenches up to 10 feet wide and 25 feet or 7.6 meter deep. The bucket wheel trenchers use a revolving bucket wheel to cut a trench up to 5 feet or about 1.5 meter wide and about 2.7 meter deep. On the other hand, there are such machines which are called the plows, can be used to cut a narrow trench and simultaneously insert a small diameter cable or pipeline in most soils. So vibratory plows such as those shown in figure 3-17 deliver a more powerful cutting action than static plows and can be used to insert utility lines in hard soil or soft rock. So here you can see that these are the examples of the trenchers. So there is this called as the chain trencher. So that means it works in one straight line and keeps trenching it, and then it can provide the vertical surfaces on the sides. And then on the other hand, there is this hydrostatic vibratory plow, which can be also used for the trenching operations. Now the trenchless technology. So in the trenchless technology, the principal categories include the pipe jacking, horizontal earth boring, and micro tunneling. Okay, so the process of pipe jacking is shown in figure 3-18. It involves forcing pipe horizontally through the soil, working from a vertical shaft. A section of the pipe is carefully aligned and advanced through the soil by hydraulic jacks braced against the shaft sides. So as the pipe advances, the spoil is removed through the inside of the pipe. After the pipe section has advanced far enough, the hydraulic rams are retracted and another section of the pipe is placed into position for installation. So the process often requires workers to enter the pipe during the pipe jacking operation. That means very large types of pipes can be placed with the pipe jacking operation. So as you can see that a very large pipe is inserted through a jacking shaft. So first of all, a shaft is made, and then from one side of the shaft, then due to the jacking operations, and then gradually the soils are removed from the front of this pipe, and then the pipe is advanced through into the side. And then the pipe reaches to the receiving shaft, then the process goes to the next shaft. So although in this case we are not in this case, we are not excavating the soil, but without the excavation of the soil, we can insert the very large size of pipes into the machine. So this is one of the trenchless technology. On the other hand, there are some other trenchless technologies in horizontal earth boring. A horizontal hole is created mechanically or hydraulically with the pipe to be installed, serving as the casing for the hole. And a track mounted thrust boring machine with percussive hammer action is also shown in this next figure. And many of these technologies utilize lasers and television cameras for hole alignment and boring controls. So a number of types of detectors are available to locate the drill head and ensure that the desired alignment and depths are being maintained. So the use of pneumatic piercing tools to create a borehole for a utility line is illustrated in figure 3-20. And then there is the micro tunneling or utility tunneling is similar to the conventional tunneling except for the tunnel size and use. So since the tunnels are used for utility systems rather than for vehicle passage, they are normally smaller than road or rail tunnels. So they differ from other trenchless methods in their use of a conventional tunnel liner and instead of using the pipe itself as a liner. So here you can see that there is this thrust boring machine with the percussive action.
Bless you.
And then here you have installing a utility line by horizontal earth boring machine. So these are some of the trenchless technologies. Okay, so the last one is the crane. So let's stop at this time and then we will continue and complete this topic in our next lesson. And we will start the next topic over here. So these three topics we will cover rather quickly within this week and the next week. And then I think after covering this topic number 7, there will be a homework number 3 that will be given to you. That's all for today. So do you have any questions?